Imagine an object in space that almost became a star. It had the gas, the gravity, the crushing compression at its core, everything it needed, except just a little more mass. So it sits in the darkness, slowly cooling, slowly fading. A failed star drifting through the void with no way to restart the process on its own. Now here's the question that keeps astrophysicists up at night. What if you could feed it? What if you could somehow dump enough matter onto this object to push it over the edge? Would it suddenly ignite, roaring to life as a true star? Or has something changed deep inside it? Something fundamental that means no amount of extra mass can ever finish the job. The answer is far stranger than you might expect. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the question at the heart of everything we're going to explore tonight. A brown dwarf is an object that almost became a star. It formed the same way stars form, from a collapsing cloud of hydrogen and helium gas. It went through the same early stages of gravitational compression. It got hot, it got dense. Gravity crushed it inward with enormous force. But somewhere along the way, the process stalled. The object didn't have quite enough mass to sustain the nuclear reactions that would have made it shine for billions of years. So it sits there in the darkness. Not quite a star, not quite a planet, something in between. Something stuck. And this raises a question that seems almost too obvious to ask. If the only thing stopping a brown dwarf from becoming a star was a shortage of mass, then what happens if you give it more? What if another brown dwarf slams into it? What if it slowly steals matter from a companion? What if it somehow gains exactly the mass it was missing? Does it finally ignite? Does it become a real star? The answer seems like it should be simple. Just add enough mass and the thing lights up. Problem solved. But nature is not that generous. The actual answer is far more complicated and far more strange than most people realize. Because what happens inside a brown dwarf over time changes the rules of the game entirely. The object doesn't just sit there patiently waiting for more mass, the way an empty fuel tank waits for gasoline. It changes. Its interior transforms in ways that fundamentally alter how it responds to being squeezed. And those transformations mean that a brown dwarf gaining mass early in its life might behave completely differently from one gaining the same amount of mass billions of years later. To understand why, we need to start at the very beginning. We need to understand what a star actually is, what it actually does deep inside its core, and why a brown dwarf fails to do the same thing. A star is not just a big glowing ball of hot gas. That description is technically true, but it completely misses what makes a star a star. What defines a star is something happening at its center. Deep in the core, where the weight of all the material above creates crushing pressure, hydrogen nuclei are being smashed together and fused into helium nuclei. This is nuclear fusion, and it is the single process that separates a star from everything else in the universe that merely glows. Here's how it works. At the center of a star like our sun, the temperature reaches about 15 million degrees. The pressure is roughly 260 billion times the atmospheric pressure on Earth's surface. Under these extreme conditions, hydrogen nuclei, which are just individual protons, are moving so fast and being squeezed so tightly that they can overcome their natural repulsion. Protons are positively charged. They repel each other the way two magnets repel when you push the same poles together. Under normal circumstances, protons would never get close enough to fuse. But at millions of degrees, they're moving fast enough and being compressed hard enough that some of them collide and stick together. When they do, a tiny amount of mass is converted into energy according to Einstein's famous relationship between mass and energy. And that energy is what makes the star shine. This process is called the proton-proton chain, often shortened to the PP chain. It's a series of reactions where individual protons are gradually combined, step by step, until you end up with a helium nucleus made of 2 protons and 2 neutrons. Along the way, some protons are converted into neutrons, positrons and neutrinos are released, and a tremendous amount of energy pours out. The Sun converts roughly 600 million tons of hydrogen into helium every single second. And it has been doing this for about 4.6 billion years. But here's the crucial part. What makes a star truly stable is not just that fusion is happening. What makes a star stable is that the fusion is self-regulating. The energy released by fusion creates outward pressure, an enormous push that fights against gravity trying to crush the star inward. In a healthy star, these two forces reach a balance. Gravity pushes in, fusion-generated pressure pushes out. The star settles into an equilibrium, a steady state where it neither collapses nor expands. It just sits there, burning hydrogen at a steady rate, glowing with a steady luminosity, maintaining itself for millions or even billions of years. This equilibrium is what defines a main sequence star. Our Sun is a main sequence star. It has been in this equilibrium for 4.6 billion years, and it will remain in it for roughly another 5 billion. The smallest true stars, the red dwarfs, can maintain this balance for trillions of years. They burn their fuel so slowly, so carefully, that they will outlast almost everything else in the universe. But they are still stars because they sustain hydrogen fusion in their cores. They have reached that critical threshold where the core temperature and pressure are high enough that the PP chain runs continuously, producing enough energy to support the star against its own gravity. Now, let's talk about brown dwarfs. Because understanding what a brown dwarf is requires understanding exactly where and why the stellar process breaks down. A brown dwarf forms the same way a star does. It begins as a clump of gas inside a molecular cloud, a vast region of cold hydrogen and helium floating in interstellar space. Gravity causes the clump to collapse. As it collapses, the gas compresses. As it compresses, it heats up. This is a fundamental principle of physics. When you squeeze gas, it gets hotter. You've experienced this yourself if you've ever used a bicycle pump. The air coming out feels warm because you compressed it. In a forming star, this compression continues until the core gets hot enough for hydrogen fusion to begin. Then the energy from fusion halts the collapse, and you have a stable star. But in a brown dwarf, something different happens. The object doesn't have enough mass. Its gravity isn't strong enough to compress the core to the temperatures needed for sustained hydrogen fusion. The core gets hot, yes. It can reach temperatures of a few million degrees, but it never quite reaches the threshold where the PP chain can run fast enough and efficiently enough to produce energy at the rate the object is losing it. The fusion sputters. It might flicker on briefly at extremely low rates, but it can never sustain itself. It can never produce enough energy to balance gravity. And without that balance, the object has no stable energy source. It will slowly radiate away the heat it built up during its formation and gradually cool down. Think about it this way. Imagine you're trying to start a campfire. If you can get the fire hot enough, it sustains itself. The heat from the burning wood dries out and ignites more wood, which produces more heat, which ignites more wood. The fire is self-sustaining. But if your wood is too damp, if your kindling is too sparse, the fire smolders. It produces some heat, some smoke, but it never catches. Eventually it dies out. A brown dwarf is like a fire that never quite caught. It smolders for a while, glowing faintly from its formation heat, but it can never sustain itself. It is destined to cool. Now, here's something extremely important that most people get wrong. The boundary between a star and a brown dwarf is not one perfectly sharp mass. There isn't some universal number where every object above it becomes a star, and every object below it becomes a brown dwarf. The boundary depends on the object's chemical composition. For an object with roughly the same chemical makeup as our Sun, what astronomers call solar metallicity, the hydrogen burning minimum mass falls at approximately 0.075 solar masses. That translates to roughly 75 to 80 times the mass of Jupiter. If the object has more mass than this, it can sustain hydrogen fusion and it becomes a true star, specifically a very low mass red dwarf. If it has less, it cannot, and it becomes a brown dwarf. But that number is not fixed for all objects everywhere. The boundaries shift depending on what the object is made of. And the key factor is something astronomers call metallicity. In astronomy, metallicity has a specific meaning. It refers to the abundance of every element heavier than helium. Carbon, oxygen, nitrogen, iron, silicon, everything that isn't hydrogen or helium gets lumped together and called metals. This sounds odd, but it makes sense because hydrogen and helium are by far the most abundant elements of the universe, and everything else is a trace ingredient. Why does metallicity matter for the hydrogen burning boundary? Because heavier elements affect how opaque the object's outer layers are. Opacity is a measure of how difficult it is for energy to escape from inside the object. More heavy elements mean more opacity, and more opacity means the object is better at trapping heat inside itself. Think of it like insulation. If you wrap a house in thick insulation, it holds onto heat more effectively. The interior stays warmer for longer. An object with higher metallicity is like a better insulated house. It holds onto its internal heat more efficiently. This means that an object with higher metallicity doesn't need to be quite as massive to maintain high enough core temperatures for hydrogen fusion. The boundary drops slightly. Instead of needing 78 Jupiter masses, maybe it only needs 73 or 74. The difference isn't enormous, but it's real. On the other hand, an object with very low metallicity, an object made almost entirely of hydrogen and helium with very few heavy elements, has less opacity. Heat escapes more easily. Its interior cools more readily, and so it needs more mass, not less, to sustain fusion. For objects with extremely low metallicity, the kind that formed in the very early universe when heavy elements barely existed, the hydrogen burning minimum mass can be significantly higher, closer to 85 or even 90 Jupiter masses. The helium abundance matters too. An object with a higher fraction of helium has a different internal structure than one with less helium. The mean molecular weight of the gas changes, which affects the relationship between pressure, density, and temperature. This shifts the boundary by a smaller amount, but it adds another variable. The point is this: There is no single magic number that determines whether an object becomes a star or a brown dwarf. The threshold is a zone, not a line. It depends on what the object is made of, and different objects are made of different things. Two objects with identical masses could end up on opposite sides of the boundary if they have different compositions. One becomes the faintest possible star. The other becomes the most massive possible brown dwarf. Same mass, different fates, because of chemistry. This matters enormously for our central question. When people ask whether a brown dwarf can become a star by gaining mass, they often imagine a simple scenario. The object is at 70 Jupiter masses. The threshold is at 78, so just add 8 more Jupiter masses and you're done. But the reality is more nuanced than that. The threshold itself isn't fixed, and as we'll see later, the brown dwarf's internal state changes with time in ways that complicate everything. Now let's talk about something that causes tremendous confusion. Brown dwarfs do undergo nuclear fusion. They are not completely inert objects, but the fusion they undergo is not the same as what happens in a star, and confusing the two leads to serious misunderstandings. The fusion that brown dwarfs can perform involves deuterium. Deuterium is a special form of hydrogen. A normal hydrogen atom, called protium, has a nucleus consisting of just one proton. Deuterium has a nucleus with one proton and one neutron. This makes it heavier than regular hydrogen, and more importantly for our purposes, it is much easier to fuse. Deuterium fusion requires a core temperature of only about 1 million degrees, compared to the roughly 3 to 4 million degrees needed for sustained hydrogen fusion via the pp chain. That's a significant difference. 1 million degrees versus 3 to 4 million degrees. Brown dwarfs can reach 1 million degrees in their cores, even if they can't reach 3 or 4 million. Any brown dwarf with a mass above roughly 13 Jupiter masses will burn deuterium in its core during the early stages of its life. This is real nuclear fusion. Deuterium nuclei combine with protons to form helium-3, and energy is released. For a while, this energy supplements the heat left over from formation, and the brown dwarf glows a little brighter than it otherwise would. But here's the catch. Deuterium is extraordinarily rare. In a typical cloud of gas from which a brown dwarf forms, deuterium makes up only about 0.002% of all the hydrogen present. That's roughly one deuterium atom for every 50,000 regular hydrogen atoms. It's a trace ingredient, and because there is so little of it, deuterium burning doesn't last long. In a typical brown dwarf, the deuterium supply is exhausted within roughly 10 to a few 100 million years, depending on the object's mass. After that, the deuterium is gone. There is no more to burn, and the brown dwarf is right back where it started, slowly cooling with no sustainable energy source. Deuterium burning is real fusion, but it is absolutely not what makes a star a star. It's a temporary phase, a brief flicker. It doesn't produce nearly enough energy to sustain the object against gravitational contraction over billions of years. Calling a brown dwarf a star because it burns deuterium would be like calling a match a furnace, because they both produce heat. The scale and the duration are completely different. There is another reaction that some brown dwarfs can undergo, and that involves lithium. Lithium is destroyed at core temperatures above about 2.5 million degrees. Objects more massive than roughly 60 to 65 Jupiter masses can reach these temperatures in their cores and will gradually destroy their lithium supply. The lithium nuclei absorb protons and are broken apart into helium nuclei, releasing a small amount of energy in the process. But lithium burning, like deuterium burning, is temporary and limited. There isn't much lithium to begin with, and the energy released is modest. Lithium burning does not sustain the object. It doesn't prevent cooling. It's just another brief episode of nuclear activity that eventually runs out. And interestingly, lithium burning has become one of the most useful tools astronomers have for identifying brown dwarfs. If you observe an object and find that it still has lithium in its atmosphere, you know its core never got hot enough to destroy it. That tells you the object is below about 65 Jupiter masses, which means it's almost certainly a brown dwarf. This technique is called the lithium test, and it has been instrumental in confirming the identity of many brown dwarfs. Now, let's talk about something that makes the brown dwarf story even more interesting: the early thermal history. When a brown dwarf first forms, it is hot. This might seem surprising given that we keep calling them failed stars, but a newly formed brown dwarf can have a surface temperature of 2,000 to 3,000 degrees. It glows a deep red, sometimes even an orange hue. It is luminous. Not as luminous as a true star, but far brighter than it will be later. In these early stages, a young brown dwarf can look almost identical to a very low mass star. If you observed a newly formed brown dwarf and a newly formed low mass red dwarf sitting side by side, you would have trouble telling them apart based on appearance alone. They can have similar temperatures, similar luminosities, similar spectra. The differences between them are hidden deep inside, in the core, where the brown dwarf is failing to sustain hydrogen fusion while the red dwarf is succeeding. This early similarity is not a coincidence. Both objects formed the same way. Both are made of the same material. Both are hot because gravitational contraction converted gravitational potential energy into thermal energy. The heat you see in a young brown dwarf isn't coming from nuclear fusion. It's coming from the formation process itself. When the cloud of gas collapsed to form the brown dwarf, gravitational energy was converted into heat, and that heat is what makes a young brown dwarf glow. It's essentially shining on leftover formation energy, spending a savings account of heat that was deposited when it was born. But here's the critical difference. A true star replaces that heat. As the formation energy radiates away, fusion kicks in and provides a new, self-sustaining energy source. The star never cools down because it has an engine running in its core that keeps replenishing the energy it loses from its surface. A brown dwarf doesn't have that engine. Or more precisely, it has a very weak engine that can burn deuterium for a while, but can't sustain itself long term. So as the formation heat radiates away into space, the brown dwarf gets cooler, and dimmer, and cooler still, and dimmer still. This cooling process never stops. A brown dwarf that formed billions of years ago is much cooler and dimmer today than it was when it was young, and the degree to which they cool is shocking. They don't just become dim, they become genuinely, almost absurdly cold for objects that were once on the verge of becoming stars. Cold enough to challenge everything you assume about what a massive ball of hydrogen and helium should feel like. The specific temperatures, when we get to them, are remarkable. This ongoing cooling has profound consequences for our central question. Because as a brown dwarf cools, something begins to change inside it. Something that will make the question of whether it can ever become a star much harder to answer than it first appeared. Deep in the core, As the temperature drops and the density remains high, a fundamentally different kind of physics starts to take over. The electrons in the brown dwarf's interior begin to enter what physicists call a degenerate state. And this degeneracy, this quantum mechanical transformation of the core material, is going to change everything. In a normal gas, like the air around you or the hot plasma inside a young brown dwarf, the behavior of the gas is governed by classical physics. Compress it and it heats up. Heat it and it expands. There's a straightforward relationship between pressure, temperature, and density. But when matter becomes degenerate, that relationship breaks down. The rules change, and the consequences for whether a brown dwarf can ever become a star are dramatic. But we'll get to that. Because the story of electron degeneracy and what it does to a cooling brown dwarf is where this entire question takes its strangest and most unexpected turn. A brown dwarf isn't just a star that ran out of luck. It's an object on a one-way journey into a state of matter where the normal rules of stellar ignition no longer apply. And understanding that journey is the key to answering whether feeding one more mass can ever undo what time has done to its core. So let's follow a brown dwarf forward in time and watch what happens inside it. Because everything about our central question, whether feeding mass to a brown dwarf can turn it into a star, depends completely on understanding what's going on in the interior of this object as millions and then billions of years roll by. We already know the starting point. A newly formed brown dwarf is hot, with a surface temperature reaching 2,000 or even 3,000 degrees Kelvin. It looks like a dim, red, faintly luminous object that can fool you into thinking it's a very low mass star. But it isn't. The glow is heat left over from formation, the thermal energy generated when a cloud of gas collapsed under its own gravity. That's all the brown dwarf has. A one-time deposit of heat, supplemented by whatever modest energy it squeezed out of deuterium burning during its first few tens of millions of years. After that, there is nothing. No engine running in the core, no nuclear reaction replacing the energy radiating from the surface. The brown dwarf is spending from a bank account that will never be refilled. And so it cools, steadily, relentlessly, without any mechanism to stop the process. The heat flows from the interior to the surface and radiates away into space as infrared light. The surface temperature drops. The luminosity dims. A brown dwarf that glowed at 2,800 degrees Kelvin when it was young might cool to 1,500 degrees after a few 100 million years. After a billion years, it might be down to 1,000 degrees. After several billion years, its surface could drop below 500 degrees Kelvin. The oldest brown dwarfs in our galaxy, objects that formed 8 or 10 billion years ago, have cooled so dramatically that some have surface temperatures of just 250 to 300 degrees Kelvin. That's roughly room temperature on Earth. If you could somehow hold one of these ancient brown dwarfs in your hand, which you obviously couldn't because it still has tens of times the mass of Jupiter, the surface wouldn't even feel hot. It would feel warm. Some of the coldest known brown dwarfs have surface temperatures below the freezing point of water. Astronomers classify brown dwarfs into spectral types based on their surface temperature. The warmest brown dwarfs are L dwarfs with temperatures between roughly 1,300 and 2,200 degrees Kelvin. Cooler than those are the T dwarfs, ranging from about 500 to 1,300 degrees Kelvin. And the coldest of all are the Y dwarfs, with temperatures below about 500 degrees Kelvin. These white dwarfs are so cool and faint that they were only discovered in the last couple of decades, when infrared space telescopes became sensitive enough to detect objects that dim. One of the coldest known brown dwarfs has a surface temperature of roughly 250 degrees Kelvin, which is about minus 20 degrees Celsius. This object is colder than many places on Earth, and it's still technically a brown dwarf, still tens of times more massive than Jupiter, still sitting there in space. But it's so cold and dim that finding it required some of the most sensitive infrared instruments ever built. This cooling is not just a surface phenomenon, it reaches all the way down to the core. In a true star, the core stays hot because fusion keeps pumping energy into it. But in a brown dwarf, the core cools along with everything else. The central temperature drops over time. A young brown dwarf might have a core temperature of several million degrees. After a few billion years, that core temperature has fallen significantly. After 10 billion years, it's fallen even further. The core is not just cooling, it's approaching a state that fundamentally changes the physics of the entire object. And that state is called electron degeneracy. To understand electron degeneracy, you need to understand something about the fundamental nature of matter at extremely high densities. And this requires a quick detour into quantum mechanics, into the strange rules that govern the behavior of particles at the smallest scales. Everything in the universe is made of particles, and those particles fall into two categories: fermions and bosons. This distinction is one of the deepest in all of physics. Fermions include electrons, protons, and neutrons, the particles that make up atoms and therefore make up you, the Earth, and brown dwarfs. Bosons include photons, the particles of light, and several other force-carrying particles. The difference between fermions and bosons lies in a property called spin, but what matters for our story is not the technical details of spin. What matters is a rule that fermions obey and bosons do not. That rule is called the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli, who formulated it in 1925. The Pauli exclusion principle states that no two identical fermions can occupy the same quantum state at the same time. This is not a suggestion. It is not a tendency. It is an absolute, unbreakable law of nature. Two electrons in the same region of space cannot have the same energy, the same position, the same spin, the same everything. If one electron already occupies a particular quantum state, no other electron can occupy that exact same state. Period. No exceptions. Ever. Under normal conditions, this rule doesn't have dramatic consequences. In ordinary matter, like the air around you or the plasma inside a young brown dwarf, there are so many available quantum states that electrons can spread out comfortably. Each electron finds its own state without any trouble. The electrons aren't bumping up against the Pauli exclusion principle because there's plenty of room in the quantum landscape for all of them. But now, imagine compressing that matter, squeezing it down to higher and higher densities. As you compress, you're forcing the electrons into a smaller and smaller volume. The number of available low-energy quantum states decreases. Electrons start filling up the available states from the bottom, the lowest energy states first. As those states fill, newly arriving electrons are forced into higher and higher energy states because the lower ones are already taken. The Pauli exclusion principle won't let two electrons share the same state, so every additional electron must go somewhere else, somewhere higher in energy. This creates a pressure, not a thermal pressure from heat, not a pressure from particles bouncing around because they're hot, but a purely quantum mechanical pressure arising from the fact that electrons literally cannot be squeezed any closer together without violating one of the most fundamental laws of physics. This pressure is called electron degeneracy pressure, and it is fundamentally different from the kind of pressure you encounter in everyday life. Let me try to make this concrete with an analogy. Imagine a parking garage with numbered spots. Each spot can hold exactly one car. When the garage is mostly empty, cars can park wherever they want. But as it fills up, drivers have to park in less convenient spots, higher floors, farther from the exit. And when every spot is taken, you simply cannot fit another car. It doesn't matter how hard you push, the garage is full. That's what electron degeneracy is like. The quantum states are the parking spots, the electrons are the cars, and when the low energy spots fill up, the electrons push back against being squeezed further. Not because they're hot, not because they're moving fast, but because there's literally nowhere for them to go. Now here's the part that matters enormously for brown dwarfs. In a normal gas, the kind of gas you find inside a young star or a young brown dwarf, pressure depends on temperature. Hot gas pushes harder. Cold gas pushes less. This is intuitive. You've experienced it. Heat air in a balloon and it expands. Cool it and it contracts. The relationship between pressure and temperature is direct and proportional. If you compress a normal gas, it heats up. If it heats up, it pushes back harder. There's a clear, dependable link between compression and temperature. But in a degenerate gas, that link is broken. Electron degeneracy pressure does not depend on temperature. It depends only on density. It doesn't matter whether the degenerate material is at 1,000,000 degrees or at 100 degrees. The degeneracy pressure is the same as long as the density is the same. The pressure arises from the quantum mechanical requirement that electrons can't share states, and that requirement doesn't care about temperature. It's a law of quantum mechanics, not a law of thermodynamics. Think about what this means. In a normal gas, if you cool it down, the pressure drops. Less heat, less pressure, so gravity can compress the gas further. This compression heats the gas back up, restoring some of the pressure. There's a dynamic cycle. Cooling leads to compression. Compression leads to heating. Heating leads to pressure. This cycle is exactly what allows stars to form in the first place. A collapsing cloud of gas compresses, heats up, compresses more, heats up more, and eventually the core gets hot enough for fusion to begin. But in a degenerate gas, cooling doesn't reduce the pressure. The pressure is quantum mechanical, not thermal. It doesn't care about the temperature. So when a degenerate brown dwarf cools, the pressure in its core stays roughly the same. The core doesn't contract, it doesn't heat up, it just gets colder while maintaining essentially the same size and the same pressure support. The cooling is completely decoupled from the structural support of the object. This is why a cooling brown dwarf doesn't spontaneously reignite. You might think that as the brown dwarf cools and contracts, the contraction would heat the core, and maybe eventually the core would get hot enough for hydrogen fusion. That's exactly what would happen if the core behaved like a normal gas. Cooling would lead to contraction, contraction would lead to heating, and the heating might eventually reach the threshold for fusion. But degeneracy breaks this cycle. The core doesn't contract when it cools, because degeneracy pressure holds it up regardless of temperature. And without contraction, there's no heating. And without heating, there's no path to fusion. The brown dwarf is not approaching ignition as it ages. It is moving away from ignition. Every year that passes makes it cooler, more degenerate, and further from the conditions needed for sustained hydrogen fusion. Time is not the brown dwarf's ally. Time is its enemy. The longer the brown dwarf exists in isolation, the harder it becomes to imagine it ever becoming a star. Now, here's something counterintuitive about degenerate objects that really drives this home. In the world of everyday experience, bigger things are heavier. A large rock weighs more than a small rock. A large balloon has more air inside than a small one. Size and mass go together. But in the world of degenerate matter, this intuition fails completely. A brown dwarf with 70 times the mass of Jupiter has roughly the same physical radius as Jupiter itself. That seems wrong. An object with 70 times more mass should be enormously larger, right? But it isn't. It's about the same size. And here's the really strange part. If you take a brown dwarf with 20 times the mass of Jupiter and compare it to one with 70 times the mass of Jupiter, the more massive one might actually be slightly smaller. Not larger, smaller. This happens because of how degeneracy pressure responds to mass. When you add mass to a degenerate object, gravity gets stronger. The object compresses. But the compression doesn't puff the object up by heating it like it would in a normal gas. Instead, the object just gets denser. The electrons are packed more tightly. The degeneracy pressure increases to match the new gravitational load, and the object settles into a new equilibrium at a slightly smaller radius. More mass, more gravity, more compression, smaller object. This is the same physics that governs white dwarfs, the dense remnants of dead stars. A white dwarf with the mass of our sun has a radius about the size of Earth. A white dwarf with more mass is actually smaller, compressed by its own stronger gravity into a denser, more compact configuration. In both white dwarfs and brown dwarfs, degeneracy pressure creates this inverted relationship between mass and size that defies everyday intuition. Why does this matter for our question? Because it tells us something profound about what happens when you try to add mass to an old, degenerate brown dwarf. The mass doesn't make the object bigger and hotter the way it would make a normal gas cloud bigger and hotter. Instead, the mass makes the object denser, more compact, and more degenerate. The added mass strengthens gravity, which compresses the core, which forces electrons into even higher energy quantum states, which increases the degeneracy pressure. But the temperature of the core doesn't rise in proportion. The compression energy doesn't go into thermal energy the way it would in a normal gas. It goes into the quantum mechanical structure of the electron gas. Imagine squeezing a rubber ball versus squeezing a block of steel. The rubber ball deforms, stores energy, and bounces back. There's a dynamic response. But the steel barely responds. It just sits there, dense and rigid. A degenerate core is like that steel block. You can push on it, you can add mass on top of it, you can increase the pressure, but the core doesn't respond with the temperature increase the way you'd need it to if you wanted fusion to begin. Now, I should be clear here. The decoupling between compression and temperature is not absolute. Even in strongly degenerate matter, adding mass does produce some temperature increase. The ions in the core, the protons and helium nuclei, still have some thermal motion. When the core is compressed, that thermal motion increases somewhat. But the increase is much smaller than it would be in a non-degenerate gas. In a normal gas, the relationship between compression and temperature is strong and direct. In a degenerate matter, the relationship is weak and attenuated. The temperature inches up when you add mass, but it doesn't leap up the way it needs to in order to reach fusion conditions. This is the fundamental problem. The more time passes, the more degenerate the brown dwarf's core becomes. And the more degenerate the core, the less effectively added mass translates into core temperature increase. It's a one-way door. Once the brown dwarf has cooled into a strongly degenerate state, the rules of the game have changed. The simple logic of add mass equals add heat equals reach fusion doesn't apply anymore. The physics has shifted underneath you. Let me put this in perspective with some numbers. A young brown dwarf, just a few million years old, still has a hot core. It hasn't had time to cool significantly. Its core is primarily supported by thermal pressure, like a normal gas. At this stage, the core is relatively responsive to changes. If you added mass to this young brown dwarf, the added gravitational compression would raise the core temperature roughly the way you'd expect. The core would get hotter. The density would increase. And if you added enough mass, the temperature might climb high enough for sustained hydrogen fusion to begin. The object would transition from a brown dwarf to a very low mass star. But now consider the same object 5 billion years later. It has cooled enormously. Its core temperature has dropped from several million degrees to perhaps just a few 100,000 degrees. The electrons in the core have become strongly degenerate. The core is now supported mostly by electron degeneracy pressure rather than thermal pressure. If you try to add the same amount of mass to this old brown dwarf, the response is completely different. The core compresses, yes. The density increases, yes. But the temperature barely budges. The compression energy is absorbed by the quantum mechanical structure of the degenerate electron gas, rather than being converted into thermal motion of the ions. The core gets denser but stays cold. It moves further into the degenerate regime rather than climbing toward fusion conditions. This is why age matters so profoundly. A brown dwarf's ability to respond to added mass changes dramatically over time. A young brown dwarf is like a campfire that almost caught. The embers are still hot. If you add more fuel quickly, the fire might roar to life. But an old brown dwarf is like embers that have gone completely cold. You can pile wood on top of cold ashes all day long, but without a spark, without heat. The wood just sits there. And in the case of a degenerate brown dwarf, the cold ashes have turned into something more like stone. The material itself has changed state, and that change makes a reignition fundamentally harder. Let me also address something people sometimes wonder about. Can a brown dwarf contract gravitationally over enough time and eventually reach fusion temperatures that way? After all, it's losing energy by radiating into space. Shouldn't that energy loss cause the brown dwarf to contract? And shouldn't the contraction eventually heat it up? In a normal gas, yes. This is called the Kelvin-Helmholtz mechanism, and it is exactly how stars work before they reach the main sequence. A forming star radiates energy, contracts, heats up from the contraction, radiates more, contracts more, and the temperature steadily climbs until fusion begins. But this mechanism requires a normal gas where cooling leads to contraction, and contraction leads to heating. In a degenerate gas, cooling does not lead to significant contraction because the degeneracy pressure holds the object up regardless of temperature. The Kelvin-Helmholtz mechanism breaks down. The brown dwarf cools, but it doesn't contract enough to generate significant heating. It is stuck, and so the brown dwarf just keeps cooling, year after year, century after century, billion years after billion years. Its surface grows cooler. its luminosity fades. If you could watch a brown dwarf over the entire history of the universe so far, you would see it go from a dim red glow to an increasingly faint ember to something barely detectable in the deepest infrared. And all the while, its core grows more degenerate, more rigid, more resistant to the kind of thermal response that would be needed for fusion to begin. There is no flaw to this cooling, at least not one that would matter on any timescale the universe has seen so far. The brown dwarf will continue cooling for trillions of years, long after the last ordinary stars have burned out. It will eventually fade to near absolute zero, approaching the temperature of the cosmic microwave background radiation. It will become a cold, dark, dense ball of degenerate matter, drifting silently through space, nearly invisible, almost undetectable. A relic of a process that started hot and bright, but never quite crossed the threshold into sustained brilliance. This is the fate of every isolated brown dwarf. Not explosion, not collapse, not dramatic transformation, just a slow, quiet, permanent fade into cold darkness. A cooling curve that only goes in one direction, down. And this is what makes our original question so much more interesting than it first appeared. We asked whether a brown dwarf can become a star by gaining mass. And now we see that the answer depends enormously on when that mass arrives. Because the object that exists a few million years after formation is fundamentally different from the object that exists a few billion years later. Same mass, same composition, same identity as a brown dwarf, but a completely different internal state. One is hot and thermally responsive, like a normal gas. The other is cold and degenerate, governed by quantum mechanics rather than classical thermodynamics. The early brown dwarf might still have a path to stardom if enough mass arrives quickly, but the old brown dwarf may have closed that door permanently, locked it with the quantum mechanical padlock of electron degeneracy, and thrown away the key. The question is no longer just how much mass can you add. The question is, how does a degenerate core respond when you try? And that question leads us to the most fascinating scenarios in all of brown dwarf astrophysics. What actually happens when you try to feed a failed star? What happens when two brown dwarfs collide and merge? Can the combined mass overcome the degeneracy that has built up in both objects? Or does the quantum mechanical state of the interior create a barrier that even a violent merger cannot breach? The answer, it turns out, lives in the complex and sometimes surprising interaction between the rate at which mass is added, the thermal state of the core at the moment it arrives, and the unyielding rules of quantum mechanics that govern matter at the highest densities. And that interaction is where we're headed next. So now we understand the problem. A brown dwarf forms below the hydrogen burning threshold. It cools. Its core becomes increasingly electron degenerate. And the more degenerate it becomes, the harder it is for any process to raise the core temperature back to the point where sustained fusion could begin. Time works against it. Every passing year moves the object further from ignition, not closer. But we haven't answered the central question yet. What if you don't let the brown dwarf sit in isolation? What if it's not alone? What if something gives it more mass? This is not a far-fetched scenario. Brown dwarfs exist in environments where gaining mass is genuinely possible. Some form in binary systems orbiting close to another star. Some are born with disks of gas and dust swirling around them, leftover material from the formation process. And sometimes, very rarely, two brown dwarfs can collide and merge into a single, larger object. Each of these scenarios offers a different pathway for a brown dwarf to gain mass, and each one produces a different outcome depending on the timing, the rate, and the internal state of the brown dwarf when the mass arrives. Let's start with the first pathway, disk accretion. When a brown dwarf forms from a collapsing cloud of gas, not all the material falls directly onto the object. Some of it ends up in orbit around it, forming a disk. This is similar to what happens when a star forms. Young stars are surrounded by protoplanetary disks, rotating pancakes of gas and dust from which planets eventually coalesce. Brown dwarfs can have these disks too, although typically smaller and less massive than those around stars. In the earliest stages of a brown dwarf's life, material from this disk can fall onto the brown dwarf, adding to its mass. This process is called accretion. Gas from the inner edge of the disk spirals inward, crashes onto the brown dwarf's surface, and becomes part of the object. This is a slow, steady process, not a sudden dramatic event. The gas trickles in over millions of years, gradually increasing the brown dwarf's total mass. Now, here's where timing becomes everything. If this accretion happens early, while the brown dwarf is still young and hot, while its core is still primarily supported by thermal pressure rather than degeneracy pressure, the added mass can have a powerful effect. The extra material increases the gravitational load on the core. The core compresses. And because the core is still behaving like a normal gas at this stage, the compression translates directly into a temperature increase. More mass means more gravity, means more compression, means higher temperature. If enough mass accretes quickly enough, the core temperature can rise to the point where sustained hydrogen fusion begins. The brown dwarf crosses the threshold and becomes a very low mass star. This is the most straightforward scenario, and it's the one that's most likely to actually work. A young brown dwarf, perhaps only a few million years old, sitting just below the hydrogen burning threshold, steadily consuming material from its formation disk until it gains enough mass to push its core temperature past the critical point. At that moment, fusion ignites. The PP chain begins running at a sustainable rate. Energy production balances energy loss. The object achieves the equilibrium that defines a main sequence star. It's no longer a brown dwarf. It has become a star. But here's the complication. Disks don't last forever. In fact, they dissipate relatively quickly. Observations of young stars and brown dwarfs show that the disks typically disperse within about 3 to 10 million years. The gas is either accreted onto the central object, blown away by radiation, or coalesces into solid bodies like planets and asteroids. After roughly 10 million years, most of the disk is gone. There's no more reservoir of gas to feed the brown dwarf. This means the window for disk accretion to push a brown dwarf across the threshold is narrow. It's only open during the first few million years, while the disk still exists, and while the brown dwarf's core is still young enough to respond thermally to the added mass. If the brown dwarf doesn't gain enough mass during this brief window, the disk disappears, the mass supply shuts off, and the brown dwarf is left to cool and become degenerate with no further prospect of gaining mass through this particular channel. The amount of mass a brown dwarf can actually gain from its disk is also limited. Brown dwarf disks are typically much less massive than stellar disks. A brown dwarf might have a disk containing only a few Jupiter masses of material, sometimes even less. If the brown dwarf formed at, say, 60 Jupiter masses and needs to reach 75 to cross the threshold, gaining 5 Jupiter masses from a disk that contains 8 isn't unreasonable. But if it formed at 40 Jupiter masses, it would need to gain 35 Jupiter masses, and that's far more than most brown dwarf disks could supply. So disk accretion is a realistic pathway only for brown dwarfs that are already very close to the boundary. Objects that formed just barely below the threshold might be able to scrape together enough extra mass from their disks to cross over. Objects that formed well below the threshold almost certainly cannot. Now let's consider the second pathway, mass transfer from a companion. Many brown dwarfs exist in binary systems, orbiting alongside another object. Sometimes that companion is another brown dwarf, sometimes it's a low-mass star, and sometimes, in rare but fascinating circumstances, the companion is a more evolved star, a red giant or even a white dwarf. In certain binary configurations, mass can flow from one object to the other. This happens through a process related to what astronomers call the Roche lobe. In a binary system, each object has a region of gravitational dominance around it. Within your Roche lobe, your gravity is stronger than your companions. Material inside your Roche lobe stays bound to you. But at the boundary of your Roche lobe, there's a point called L1, the first Lagrange point, where the gravitational pulls of both objects are exactly balanced. If one star expands and its outer layers reach the L1 point, that material can spill over into the companion's Roche lobe, falling onto the companion and adding to its mass. This is most commonly seen in binary systems, where one star has evolved into a red giant. Red giants are enormously bloated. They can expand to hundreds of times the diameter of our Sun. If a brown dwarf orbits close enough to a red giant companion, the giant's outer layers can overflow the L1 point and cascade onto the brown dwarf. The mass transfer can be substantial, potentially delivering many Jupiter masses of hydrogen-rich material over time. But here's the question that matters. When does this mass transfer happen? A star doesn't become a red giant until late in its life. For a Sun-like star, this happens roughly 10 billion years after formation. For a slightly more massive star, it might happen after just a few 100 million or a few billion years. But in any case, by the time the companion star has evolved into a red giant and begun transferring mass, the brown dwarf has been cooling for a very long time. It's not a young, hot, thermally responsive object anymore. It's an old, cold, degenerate one. And this is where the physics we discussed becomes critical. When mass falls onto an old, degenerate brown dwarf, the response is muted compared to what would happen with a young one. The incoming material crashes onto the surface and compresses the object further. The density increases. But because the core is degenerate, the temperature increase is far less dramatic than it would be in a non-degenerate gas. The compression energy goes primarily into the quantum mechanical structure of the electron gas rather than into thermal energy. Does this mean it's impossible? Not necessarily, but it means the path is harder, much harder. The brown dwarf might need to gain significantly more mass than a simple calculation would suggest, because each additional unit of mass is less efficient at raising the core temperature when the core is degenerate. It's like trying to heat a room where the walls are made of superconducting insulation that absorbs heat without getting warmer. You can pour energy in, but the temperature barely moves. There's another complication with mass transfer from a companion. The rate matters enormously. If mass transfers slowly, trickling onto the brown dwarf over hundreds of millions of years, the object has time to adjust its structure between each small addition. It settles into a new equilibrium at each step, with slightly higher density and only marginally higher temperature. The degeneracy remains strong throughout. The core never gets a dramatic kick in temperature because each individual mass addition is too small to overwhelm the degenerate response. But if mass transfers rapidly, dumped onto the brown dwarf in a geologically short period of, say, 10,000 or 100,000 years, the story changes somewhat. A rapid influx of mass compresses the core faster than the object can fully adjust. The compression happens on a timescale shorter than the thermal timescale, the time it takes for heat to redistribute through the interior. This can temporarily boost the core temperature more effectively than slow accretion would. The core gets squeezed hard and fast before the degenerate structure can fully absorb and redistribute the energy. Whether this rapid compression is enough to trigger fusion depends on specific details. How much mass is transferred, how quickly, how degenerate the core was before the transfer began, what the composition is. These details vary from system to system. There's no single answer that applies to all cases, but the general principle holds. Fast mass gain on a less degenerate core gives you the best chance. Slow mass gain on a highly degenerate core gives you the worst. Now let's talk about the most dramatic scenario of all. What happens when two brown dwarfs collide and merge? This is the most violent and energetic pathway for a brown dwarf to gain mass. And it's also the one that has the most potential to overcome the degeneracy barrier. Because in a merger, we're not talking about a slow trickle of gas. We're talking about two massive objects smashing together in a cataclysmic event that releases an enormous amount of energy in a very short time. How does this happen? Brown dwarfs in a closed binary system can gradually spiral toward each other. This in-spiral happens because the orbiting objects lose energy over time through gravitational interactions, tidal friction, and, in some cases, the emission of gravitational waves, although gravitational wave emission is extremely weak for objects as light as brown dwarfs. More commonly, tidal interactions and angular momentum loss through magnetic braking or interactions with surrounding material cause the orbit to shrink. Over millions or billions of years, the two brown dwarfs get closer and closer until eventually they touch, their surfaces making contact, their material beginning to mix, and then, in a relatively short time, they merge into a single object. But the word merge makes this sound far too gentle. Let's talk about what actually happens during one of these events, because the physical details of the collision matter enormously for whether the merged object can ignite fusion. When two brown dwarfs in a decaying orbit finally make contact, the event unfolds over a period of hours to days, not the millions of years that characterize most astronomical processes. The two objects don't simply melt into each other like two drops of water merging on a tabletop. They collide with enormous kinetic energy. The relative velocities of contact can be tens or even hundreds of kilometers per second, depending on how close the orbit was before the final plunge. That kinetic energy has to go somewhere, and where it goes determines whether the merged object has any chance of becoming a star. The first thing that happens is that the outer layers of both objects are violently disrupted. Material from each brown dwarf crashes into material from the other, creating powerful shock waves that ripple through the combined structure. These shocks are critically important. A shock wave is a sudden, dramatic compression of material, a wall of pressure moving through the gas faster than the speed of sound. When a shock passes through a region, it compresses and heats that region almost instantaneously. In a non-degenerate gas, this shock heating can raise temperatures enormously. In a degenerate gas, the heating is less efficient, but it still happens. The shock deposits energy into the material, and some fraction of that energy becomes thermal energy, raising the temperature. The question is whether the shocks can penetrate all the way to the core. If the shocks dissipate in the outer envelope, heating only the non-degenerate surface layers, the core remains cold and degenerate. The outer layers get hot, maybe spectacularly hot for a brief time, but the core, where fusion needs to happen, stays essentially unchanged. On the other hand, if the shocks are strong enough to propagate deep into the interior, they can deposit energy directly into the degenerate core, giving it a thermal kick that surface accretion alone could never provide. Whether shocks reach the core depends on several factors. The geometry of the collision matters. A head-on collision, where the two objects strike each other along the line connecting their centers, produces the strongest central compression. An off-center or glancing collision distributes the energy more broadly, with less reaching the core. The spin of each object matters too. If both brown dwarfs are rotating rapidly, angular momentum must be shed or redistributed during the merger. Some of that angular momentum can support the merged material against collapse, creating a temporary disk or torus of material around the central remnant rather than allowing everything to compress directly onto the core. This delays and weakens the compression, giving the degenerate structure more time to absorb and redistribute the energy. Computer simulations of brown dwarf mergers run using sophisticated hydrodynamic codes that track the motion of gas in 3 dimensions, show that the outcome is sensitive to these geometric and rotational details. Simulations of nearly head-on mergers between moderately degenerate brown dwarfs tend to produce the highest central temperatures, sometimes exceeding the fusion threshold. Simulations of highly off-axis mergers with significant angular momentum tend to produce lower central temperatures, with more energy going into the envelope and the temporary disk rather than into the core. The angular momentum problem is worth emphasizing because it connects to something observable. Real brown dwarf binary systems have measurable orbital parameters. We can determine how close the two objects are, how fast they're orbiting, and how much angular momentum the system contains. These measurements tell us something about what kind of merger the system would eventually produce if the orbit decays far enough. Astronomers have identified a number of brown dwarf binary systems with separations small enough that a future merger is at least plausible. Some of these systems have orbital periods of just a few days, meaning the two brown dwarfs are orbiting each other at very close range, separated by only a few times the radius of the objects themselves. At such close separations, tidal interactions are strong, and the orbit can decay on timescales of billions of years. These are the systems where mergers are most likely to eventually occur. But there's an important observational fact that constrains how common these mergers can be. Surveys of brown dwarfs have found that tight binaries, systems where two brown dwarfs orbit within about 3 astronomical units of each other, are relatively rare. Most brown dwarf binaries have wider separations, too far apart for their orbits to decay significantly within the age of the universe. This means that while brown dwarf mergers are physically possible, they are probably uncommon events. Most brown dwarfs will never encounter another brown dwarf closely enough to merge. They will cool alone, undisturbed, forever. The combined mass of the merged object can easily exceed the hydrogen-burning minimum mass. If each brown dwarf had 40 Jupiter masses, the merged object has roughly 80 Jupiter masses, well above the threshold. If each had 50, the result is 100 Jupiter masses, significantly above the boundary for any composition. In terms of raw mass, the merged object has enough to be a star, but does having enough mass guarantee that hydrogen fusion will begin? This is the heart of the question, and the answer depends on the thermal and degeneracy state of the merging objects, and on the dynamics of the merger itself. Let's consider the best case scenario first. Two relatively young brown dwarfs, perhaps each only a few 100 million years old, merge. At this age, their cores haven't had time to become strongly degenerate. They're still somewhat warm. Their interiors still retain a significant fraction of thermal pressure support. When these two young objects merge, the collision is violent. An enormous amount of gravitational energy is released as the two objects combine. This energy heats the merged object dramatically. The core of the newly formed single object is compressed by the combined mass of both progenitors, and because the core isn't strongly degenerate, this compression translates efficiently into temperature increase. The core temperature can jump to millions of degrees, potentially reaching or exceeding the threshold for sustained hydrogen fusion. In this scenario, the merged object can genuinely become a star. The merger provides a massive, sudden injection of gravitational energy. The core is hot enough and non-degenerate enough to convert that energy into thermal energy. The temperature exceeds the fusion threshold. The PP chain ignites. Energy production begins. And because the merged object's mass is well above the hydrogen burning minimum, the fusion is self-sustaining. The object settles onto the main sequence as a very low mass red dwarf. It's a real star, born not from a single collapsing cloud, but from the merger of two objects that individually failed. But now let's consider the worst case scenario. Two ancient brown dwarfs, each 10 billion years old, merge. These objects have been cooling for 10 billion years. Their cores are profoundly degenerate. Their central temperatures have dropped to just hundreds of thousands of degrees, or even lower. The electrons are packed into the lowest available quantum states. The cores are rigid, dense, quantum mechanically locked. When these two ancient objects merge, the collision is still violent. Energy is still released. The impact still generates an enormous amount of heat, but the merged core is now highly degenerate. And degenerate matter does not respond to compression the way normal matter does. The energy from the collision goes partly into heating the outer layers, which are less degenerate, and partly into the quantum mechanical structure of the degenerate core. The core temperature rises, but not nearly as much as it would if the core were a normal gas. The degeneracy acts like a buffer, absorbing the energy of the collision without translating it proportionally into temperature. Whether the core temperature rises enough to initiate sustained hydrogen fusion in this scenario is uncertain. It depends on the details. How degenerate were the individual cores before the merger? How violent was the collision? Was the merger a slow spiraling in over thousands of years, or a relatively rapid smash over just a few orbits? Did the merger create shocks that propagated into the core and deposited energy there, or was most of the shock energy dissipated in the outer envelope? Theoretical models and computer simulations of brown dwarf mergers suggest a range of outcomes. Some simulations find that even old, degenerate brown dwarfs can be pushed to fusion if the merger is violent enough, and the combined mass is significantly above the threshold. The reasoning is that even though degeneracy suppresses the temperature response, a sufficiently large amount of energy dumped into the core sufficiently quickly can overcome this suppression. The core temperature doesn't need to rise as much as it would in a normal gas, because the density in a degenerate core is already extremely high. Fusion rate depends on both temperature and density, and the density in a merged degenerate core is enormous, so even a modest temperature increase might be enough to push the fusion rate above the threshold for sustainability. Other simulations and theoretical analyses are less optimistic. They suggest that in the most extreme cases, when the merging objects are very old and very degenerate, the merged core might remain below the fusion threshold even though the total mass is well above the hydrogen burning minimum. The object would then be something extraordinary. A brown dwarf with a mass that should make it a star, but that cannot sustain fusion because its internal structure, shaped by billions of years of cooling and degeneracy, prevents the core from reaching the necessary temperature. The truth is that the outcome likely depends on a continuum of factors rather than a single yes or no condition. There's a spectrum of possibilities. At one end, young and warm brown dwarfs merging early, the answer is almost certainly yes, fusion can begin. At the other end, ancient and profoundly degenerate brown dwarfs merging after 10 billion years of cooling, the answer is genuinely uncertain, and it might be no for some configurations. Let me emphasize something about the rate and violence of mass addition, because this is a thread that runs through every scenario we've discussed. Whether the mass comes from a disk, from a companion star, or from a merger, the rate at which it arrives is at least as important as the total amount. Consider an analogy. Imagine a block of ice sitting in a cold room. Place a candle near it and the ice barely melts. The cold room pulls heat away almost as fast as the candle provides it. This is like slow accretion onto an old degenerate brown dwarf. The mass trickles in, the core gets slightly compressed, slightly warmer, but the degenerate structure absorbs and redistributes the energy without dramatic thermal change. Now throw that same block of ice into a blast furnace. The ice cannot absorb and redistribute the heat fast enough. It melts, then vaporizes, almost instantly. This is more like a violent merger, a catastrophic event where an enormous amount of energy is delivered to the core, faster than the degenerate structure can fully respond. The degeneracy is still there, still resisting, but the energy input is so large and so fast that the core temperature rises significantly despite that resistance. In physics, there's a concept called the thermal timescale, the time it takes for heat to flow through a body and for the body's temperature to adjust to a new energy input. For a brown dwarf, the thermal timescale can be millions of years. If mass is added on a timescale much shorter than this, the core doesn't have time to adjust. The energy piles up locally. Temperature spikes can occur in regions that haven't had time to conduct their heat away. These local hotspots might reach fusion conditions even if the core as a whole is still degenerate and cold. This is why mergers are the most promising pathway for turning an old brown dwarf into a star. A merger delivers mass on a timescale of hours to years, far shorter than the thermal timescale of millions of years. The energy input is massive and rapid. The core is shocked, compressed, heated, all before it can settle into a new degenerate equilibrium. There's a window during the merger event where the core is temporarily out of equilibrium. temporarily hotter than its degeneracy would normally allow. And if the temperature during that window exceeds the fusion threshold, and if the total mass is sufficient to sustain fusion once it begins, then the object can transition to a star. But there's a critical additional question that we haven't addressed yet. What determines whether a brief post-merger ignition becomes permanent? Because even if the core temperature briefly exceeds the fusion threshold during the violent chaos of a merger, that doesn't automatically mean the object becomes a stable star. The fusion has to sustain itself. It has to produce enough energy to maintain the core temperature above the threshold, even after the merger energy dissipates. If it can't do that, the fusion dies and the object cools back down. Here's what determines the outcome. In a normal star, fusion is self-regulating through a feedback loop. The fusion produces energy, which produces pressure, which supports the star against gravity, which maintains the core conditions for more fusion. The loop is stable. Remove a little energy and the core contracts slightly, heats up slightly, and fusion increases to compensate. Add a little energy and the core expands slightly, cools slightly, and fusion decreases. The star naturally returns to equilibrium. But in a recently merged object with a partially degenerate core, this feedback loop may not work properly. In degenerate material, the pressure doesn't respond to temperature changes the way it does in normal gas. If fusion briefly ignites in a degenerate core, the energy it produces may not create enough additional pressure to expand and regulate the core. Instead, the energy might be conducted away, absorbed by the degenerate electron structure, or radiated from the surface without ever establishing the self-regulating feedback loop that a stable star requires. The fusion burns for a while, consuming hydrogen, producing energy, but that energy leaks away without building the pressure structure needed for permanence. Eventually, the merger-deposited heat dissipates, the core temperature falls below the threshold, and the fusion stops. For the fusion to become permanent, the core needs to transition out of degeneracy. The thermal energy from fusion has to become dominant over the degeneracy pressure, effectively lifting the core out of its degenerate state and back into a regime where normal gas behavior takes over. Only then can the self-regulating feedback loop establish itself. Only then can the object settle onto the main sequence as a true star. Whether this transition happens depends on the balance between the fusion energy production rate and the rate at which the degenerate core can absorb and redistribute that energy. If fusion produces energy faster than degeneracy can swallow it, the core heats up, degeneracy weakens, and the object transitions to a star. If degeneracy absorbs energy faster than fusion produces it, the core stays locked in its quantum mechanical state, and the fusion eventually dies. There's also an intermediate scenario. What if a companion star evolves, expands rapidly, and dumps substantial material onto the brown dwarf over thousands to tens of thousands of years? The outcome depends on the same competition between the mass addition timescale and the brown dwarf's thermal timescale that governs every other scenario. Faster than the core can adjust, and you might get ignition. Slower, and the degenerate structure absorbs everything. The critical question in every scenario comes down to the same fundamental physics. Can you deliver enough energy to the core fast enough to raise the temperature past the fusion threshold before the degenerate structure absorbs and redistributes that energy into the quantum mechanical electron gas? If yes, the brown dwarf becomes a star. If no, it absorbs the mass, becomes denser, possibly becomes slightly warmer for a time, but ultimately settles back into a degenerate state at a higher mass. It becomes something new and strange, a brown dwarf that is more massive than it should be, more massive than the hydrogen burning limit for its composition, yet still not a star. And that strange possibility, the idea of a brown dwarf sitting above the mass threshold but still failing to sustain fusion, is one of the most fascinating theoretical outcomes in all of stellar astrophysics. It would be an object that defies the simple classification we usually rely on. Not a star, because it's not fusing hydrogen. Not a typical brown dwarf, because its mass exceeds the boundary where fusion should be happening. It would be something caught between categories, a product of a unique history that left it stranded in a physical state that normal formation pathways never produce. Whether such objects actually exist in the universe is an open question. We haven't confirmed any, but the theoretical arguments for their possibility are sound. If two old, highly degenerate brown dwarfs merge, and if the merger dynamics don't deposit enough energy into the core to trigger sustained fusion, the result would be exactly this kind of object. An overmassive brown dwarf. A massive failed star that had a second chance and still couldn't quite make it. The universe doesn't always give you clean answers. Sometimes the boundary between what an object is and what it could have been is blurred by history. The mass is there. The raw ingredients are there. But the path the object took, the billions of years it spent cooling into degeneracy before the mass arrived, changed the rules. And those changed rules might mean that crossing the threshold on paper doesn't guarantee crossing it in reality. So the picture that emerges is nuanced. The answer to whether a brown dwarf can become a star isn't simply yes or no, it's conditional. It depends on when, how fast, and how much. It depends on the thermal history of the object, the degeneracy of its core, the violence of the mass addition event, and the competition between gravitational energy and quantum mechanical resistance. In some scenarios, the transformation works. In others, it may not. And in the most extreme cases, you might end up with something the universe has never categorized before. An object that sits in the gap between the labels, challenging our neat definitions and reminding us that nature is always more complicated than the boxes we try to put it in. So let's take stock of where we are. We've followed the life of a brown dwarf from its formation in a collapsing cloud of gas all the way through its long, slow cooling into an increasingly degenerate state. We've explored three pathways by which a brown dwarf could gain mass. Disk accretion early in life, mass transfer from a companion star, and the dramatic violence of a direct merger with another brown dwarf. And we've seen that the outcome depends not simply on how much mass is added, but on when it arrives, how quickly it's delivered, and what the internal state of the brown dwarf is at the moment of delivery. Now we need to confront the strangest implication of everything we've discussed. The theoretical possibility that an object could exist with a mass above the hydrogen burning threshold and still not be a star. This idea sounds almost contradictory. We've been taught, correctly, that there's a mass boundary separating brown dwarfs from the lowest mass stars. Above roughly 75 to 80 Jupiter masses, an object should sustain hydrogen fusion. Below that, it can't. This boundary has been confirmed through decades of observations and theoretical calculations. It works. It predicts real behavior in real objects. When astronomers find an object above the boundary, it's almost always fusing hydrogen. When they find one below, it's almost always not. but this boundary was derived assuming normal formation. It assumes the object formed from a single collapsing cloud of gas, went through a standard gravitational contraction, and either reached fusion conditions or didn't. It assumes a smooth, uninterrupted history. It does not account for what happens when an object reaches high mass through an unusual pathway, specifically when it spends billions of years as a low-mass brown dwarf, cooling into deep degeneracy, and only then gains additional mass through a merger or accretion event. An overmassive brown dwarf would be an object that arrived at its current mass through a non-standard pathway. It formed below the threshold. It cooled. It became degenerate. And then, perhaps through a merger with another degenerate brown dwarf, it gained enough mass to exceed the threshold. But because its core was profoundly degenerate at the time of the mass gain, the temperature increase was insufficient to ignite sustained hydrogen fusion. The object now sits above the mass boundary, possessing all the raw material it needs to be a star, but unable to use it because its internal physics won't cooperate. Think about it this way. A normal star that formed at 80 Jupiter masses achieved fusion because its core was hot and non-degenerate during the critical contraction phase. The compression translated smoothly into temperature increase. The fusion threshold was crossed while the core was still responsive. But a hypothetical overmassive brown dwarf reached 80 Jupiter masses only after its core had already become degenerate. The same mass, the same composition, but a completely different thermal and quantum mechanical history. And that history makes all the difference. This is a genuinely important point about how nature works. The final state of an object doesn't depend only on its current properties. It depends on how it got there. Two objects can have identical masses and compositions but behave completely differently because they took different paths through time. In physics, this is sometimes called path dependence. The history matters, not just the endpoint. Now, I should be careful here. Overmassive brown dwarfs are a theoretical prediction, not a confirmed observational population. No astronomer has pointed a telescope at an object and definitively said that this particular body has 90 Jupiter masses, but is not fusing hydrogen because of its degeneracy history. The theoretical arguments for their existence are sound, grounded in well-understood physics of electron degeneracy and stellar structure. But confirming that such objects actually exist in the universe requires observations, and those observations are extraordinarily difficult. Why are they so difficult? Because distinguishing an overmassive brown dwarf from a very low-mass star is one of the hardest problems in observational stellar astrophysics. Let's talk about how astronomers classify these objects in practice. Because the tools they use reveal just how subtle the distinction between star and brown dwarf can be, especially near the boundary. The most basic property astronomers measure is luminosity, how much total energy the object is emitting per second. Stars have a steady luminosity because they have a sustained energy source, hydrogen fusion. Their luminosity depends primarily on their mass. More massive stars are more luminous. Less massive stars are less luminous. But even the faintest stars, the lowest mass red dwarfs, sitting just above the hydrogen burning threshold, have a stable luminosity that they maintain for trillions of years. They are dim, yes. Incredibly dim, but consistently dim. Their brightness doesn't change much over time because fusion is continuously replenishing the energy they radiate. Brown dwarfs, by contrast, have a luminosity that decreases over time. Because they have no sustained energy source, they fade. A young brown dwarf can be surprisingly luminous, but give it a few billion years and it dims enormously. This declining luminosity is one of the key observational signatures of a brown dwarf. But here's the problem. If you observe an object at a single moment in time, you can't easily tell whether its current luminosity is stable or declining. You'd need to watch it for millions of years to see the decline directly. And obviously nobody has that kind of patience. Instead, astronomers rely on indirect clues. They look at the object's temperature, its spectrum, and its chemical composition, piecing together evidence to determine whether it's sustaining fusion or slowly fading. Surface temperature is one clue. Stars on the main sequence have surface temperatures that are roughly stable over time. A very low mass red dwarf might have a surface temperature of about 2,300 to 2,800 degrees Kelvin. It will maintain this temperature for as long as it's fusing hydrogen. Brown dwarfs, on the other hand, start hot and cool continuously. A young brown dwarf might have a surface temperature similar to a low-mass star, but an old brown dwarf can be much cooler, dropping into the T-dwarf or Y-dwarf range at temperatures below 1,000 degrees Kelvin. So if you find an object with a very low surface temperature, say 500 degrees Kelvin, you can be fairly confident it's a brown dwarf, because no star gets that cool while still on the main sequence. But near the boundary, where brown dwarfs and the lowest mass stars overlap in temperature, the distinction gets murky. A young, relatively massive brown dwarf might have the same surface temperature as a very old, very low mass star. They can look alike. Their spectra can be similar. You can't easily tell them apart based on temperature alone. This is where the lithium test becomes invaluable. Remember, lithium is destroyed in objects that reach core temperatures above about 2.5 million degrees. Any true star, even the lowest mass one, eventually reaches this temperature in its core and destroys its lithium. So if you observe an object and find lithium absorption lines in its spectrum, you know the object's core never got hot enough to destroy lithium. This tells you the object is below roughly 65 Jupiter masses, firmly in the brown dwarf range. But the lithium test has limitations. It works well for identifying objects that are clearly below the hydrogen burning boundary. If you detect lithium, the object is almost certainly a brown dwarf. But the absence of lithium doesn't automatically mean the object is a star. Objects between about 65 and 75 Jupiter masses can destroy lithium without sustaining hydrogen fusion. They reach temperatures hot enough to burn lithium during their early contraction phase, but not hot enough to sustain the PP chain long term. So an object without lithium could be either a very low mass star or a relatively massive brown dwarf that destroyed its lithium but couldn't sustain hydrogen fusion. This creates a frustrating gap in our diagnostic toolkit. Right near the boundary, between about 65 and 85 Jupiter masses, the standard tests start to break down. Temperature isn't diagnostic by itself. Luminosity requires knowing the age, which is often uncertain. The lithium test loses its discriminating power. You need multiple lines of evidence, combined with theoretical models of how objects at different masses should evolve, to make a classification. Now, imagine trying to identify an overmassive brown dwarf in this context. The object has, say, 90 Jupiter masses. A normal 90 Jupiter mass object should be a star, fusing hydrogen with a stable luminosity and temperature on the main sequence. But our hypothetical overmassive brown dwarf, which reached 90 Jupiter masses through a late merger of two degenerate objects, isn't fusing hydrogen. It's cooling. Its luminosity is declining. Its temperature is dropping. How would this object look? Initially, right after the merger, the event would produce a brief burst of luminosity as gravitational energy is released. The object would temporarily appear brighter and hotter than expected. But after the merger energy dissipates, the object would begin cooling, just like any other brown dwarf. Its luminosity would decline, its temperature would drop. Over time, it would come to resemble a brown dwarf, not a star, despite having a mass that should put it firmly in the stellar category. If an astronomer observed this object a few billion years after the merger, they would see something puzzling, an object that appears to be a brown dwarf, fading, cooling, showing spectral characteristics associated with brown dwarfs, but with a mass, if they could measure it, that seems too high. Measuring mass is the key, and that requires either a dynamical mass measurement from orbital motion in a binary system, or a very precise determination of the object's luminosity combined with detailed atmospheric modeling. Let's talk about these mass measurement techniques in a bit more detail, because they are the key to the entire problem. Without precise mass measurements, overmassive brown dwarfs could be sitting in our data right now, and we would have no way of recognizing them. The most reliable method for measuring the mass of a brown dwarf is the dynamical method using binary systems. If a brown dwarf orbits another object, whether that's a star, another brown dwarf, or anything else with measurable gravity, the orbital motion of the two objects reveals their masses. This is Newton's gravity at work. Two objects orbit each other with a period and separation that depend on their combined mass. If you can measure the orbital period and the size of the orbit, you can calculate the total mass of the system. And if you can measure how much each object moves relative to the other, you can determine the individual masses separately. There are several ways to make these measurements. Radial velocity observations track the Doppler shift of spectral lines as an object moves toward and away from us during its orbit. As the brown dwarf orbits, its light gets slightly bluer when it's moving toward us and slightly redder when it's moving away. By measuring these tiny shifts, astronomers can determine the orbital speed and, from that, constrain the masses involved. This technique has been enormously successful for detecting exoplanets, and it works for brown dwarfs too, although the measurements are more challenging because brown dwarfs are much fainter than stars. Astrometric monitoring takes a different approach. Instead of measuring changes in the light's wavelength, you measure changes in the object's position on the sky. As a brown dwarf orbits a companion, it traces out a tiny ellipse on the sky. By measuring this wobble precisely over months or years, you can determine the orbital parameters and calculate the masses. The Gaia spacecraft, which has been mapping the positions and motions of billions of objects in our galaxy with extraordinary precision, is particularly powerful for this kind of measurement. Gaia can detect the astrometric wobble caused by a companion even when the companion itself is too faint to see directly. Over its mission lifetime, Gaia is expected to reveal thousands of previously unknown brown dwarf companions through their gravitational influence on the stars they orbit. In rare and fortunate cases, a brown dwarf binary system is oriented so that the two objects pass in front of each other as seen from Earth. These are called eclipsing binaries. When one object passes in front of the other, the total light from the system dips. The timing, depth, and shape of these dips reveal the sizes of both objects, and, combined with radial velocity measurements, their masses. Eclipsing brown dwarf binaries are exceptionally valuable because they provide both mass and radius measurements simultaneously, two independent constraints that can be compared against theoretical models. Only a handful of eclipsing brown dwarf systems are known, but each one provides an extraordinary window into the properties of these objects. There is one more technique worth mentioning, although it's rarer and harder to apply. Gravitational microlensing occurs when a massive object passes between us and a more distant background star. The gravity of the foreground object bends and magnifies the light from the background star, creating a temporary brightening event. The duration and shape of this brightening depend on the mass of the foreground object. Microlensing events involving brown dwarfs have been detected, and they provide mass estimates for objects that would otherwise be completely invisible because they emit so little light of their own. The challenge with microlensing is that each event is unique and unrepeatable. The alignment of foreground and background objects is a one-time coincidence. You can't go back and observe the same event again. But large surveys monitoring millions of stars simultaneously can catch many of these events and build up a statistical picture of the brown dwarf population. All of these techniques are improving rapidly. The James Webb Space Telescope, with its extraordinary sensitivity in the infrared, is pushing our ability to detect and characterize the faintest, coldest brown dwarfs to entirely new limits. Objects that were invisible to every previous telescope are now being revealed. And the combination of Webb's infrared sensitivity with Gaia's astrometric precision is creating for the first time the possibility of measuring masses for very cold, very old brown dwarfs that might include overmassive objects formed through ancient mergers. If the overmassive brown dwarf happened to be in a binary system where its orbital motion could be measured, astronomers could calculate its mass directly. And if that mass turned out to be well above the hydrogen burning boundary, while the object's luminosity and temperature were clearly substellar, the contradiction would be apparent. The object would have too much mass to be a brown dwarf under normal assumptions, yet it would behave exactly like one. This kind of discovery hasn't been confirmed yet, but it's not impossible. Our surveys of brown dwarfs are still incomplete. Most brown dwarfs are very faint and hard to detect. The ones we've found tend to be either relatively nearby or relatively young, and therefore still somewhat luminous. Ancient, cold brown dwarfs formed from mergers billions of years ago would be extremely difficult to find. They would be dim, cold, and rare. We might have already detected some without realizing what they are, because we would need both a precise mass measurement and a clear demonstration that the object is not sustaining fusion to identify it as overmassive. There's one more piece of observational context that matters for understanding how likely overmassive brown dwarfs are. It's something called the brown dwarf desert. This isn't a place, it's a statistical pattern. When astronomers survey sun-like stars and look for companions orbiting close to them, within about 5 astronomical units, they find planets frequently and stellar companions frequently, but brown dwarfs are strangely rare. There's a gap in the companion mass distribution right in the brown dwarf range, between roughly 13 and 80 Jupiter masses. Far fewer companions are found at these masses than you would expect if nature distributed masses randomly. This relative emptiness is what astronomers call the brown dwarf desert. The brown dwarf desert tells us something important about how these objects form and where they end up. It suggests that brown dwarfs and giant planets form through different mechanisms, and that the conditions which produce brown dwarfs don't often place them in close orbits around sun-like stars. Brown dwarfs that form in close binary systems tend to form alongside other low-mass objects, not alongside sun-like stars. This has implications for the merger scenario. If most brown dwarf binaries are pairs of brown dwarfs, rather than a brown dwarf orbiting a sun-like star, then the mergers most likely to occur are exactly the kind we've been discussing. Two brown dwarfs spiraling together and combining. But the brown dwarf desert also tells us these close pairings are not overwhelmingly common. The conditions for a future merger exist, but they are not the norm. Most brown dwarfs form either in isolation or in wide binaries that will never decay enough to produce a merger within the age of the universe. This means that even if the physics allows overmassive brown dwarfs to exist, the astrophysical circumstances that produce them are probably rare. They would require two brown dwarfs to form close enough together for their orbit to decay, to survive long enough for the merger to occur, and for the merger to fail to produce sustained fusion. Each of these conditions is individually uncommon. Together they suggest that overmassive brown dwarfs, if they exist at all, are needle-in-a-haystack objects. Rare, faint, cold, and hiding among populations of normal brown dwarfs that already challenge our ability to detect them. Finding one would be a triumph of observational astronomy, a confirmation that the strange theoretical predictions about degeneracy and path dependence are not just mathematical curiosities but descriptions of real objects in the real universe. There is also a subtlety that makes the theoretical predictions uncertain. Even in the most extreme merger scenarios where two highly degenerate brown dwarfs combine, some degree of hydrogen fusion might occur, at least temporarily. The merger heats the core, and even in degenerate matter, some temperature increase happens. If the temperature rises enough, hydrogen fusion might ignite briefly. But briefly is the key word. If the fusion cannot sustain itself, if the energy it produces is insufficient to maintain the core temperature against the degenerate structure's tendency to absorb and redistribute heat, then the fusion will flicker on and die again. The object would experience a brief episode of nuclear burning, perhaps lasting thousands or millions of years, and then fade back into the cooling track. This creates a spectrum of possible outcomes, rather than a clean binary of star versus non-star. At one extreme, a young merger produces sustained, permanent fusion. The object becomes a true star and stays one. At the other extreme, an ancient merger fails to ignite fusion at all. The object remains a brown dwarf despite its high mass, and in between, there might be objects that experience temporary, unsustainable fusion, burning hydrogen for a while before the degeneracy wins and the fire goes out. These intermediate objects would be especially hard to classify. Are they stars? They fused hydrogen, but only temporarily. Are they brown dwarfs? They have masses above the boundary, and they did sustain fusion for a while. There's something in between, objects that defy our neat categories. This brings us to the qualified answer to our original question. Can a brown dwarf ever become a star? The answer is yes, but only under specific conditions. And no, not under others. And maybe in a frustrating grey zone between the two. If a brown dwarf gains mass early in its life, while its core is still hot and primarily supported by thermal pressure, then yes. The core responds to the added mass with a proportional temperature increase. Fusion ignites, the object becomes a main sequence star. This is most likely through rapid disk accretion or an early merger before significant cooling has occurred. If a brown dwarf gains mass late in its life, after billions of years of cooling have left its core profoundly degenerate, the situation is much less certain. Slow accretion from a companion almost certainly fails. Even a violent merger between two ancient degenerate objects might fail, leaving behind an overmassive brown dwarf that sits above the threshold on paper but cannot cross it in practice. And crucially, an isolated brown dwarf never spontaneously ignites. This is perhaps the most important single fact in this entire story. A brown dwarf sitting by itself in space, with no companion, no disk, no source of additional mass, will never become a star. It doesn't matter how long you wait. 1,000,000 years, 1,000,000,000 years, 1,000,000,000,000 years. The brown dwarf will not ignite. It will only cool. It will only become more degenerate. Every year that passes moves it further from the conditions needed for fusion, not closer. The cooling is irreversible. The degeneracy only deepens. The door to stardom closes more tightly with every passing epoch. This is fundamentally different from what many people imagine when they hear about brown dwarfs. There's a common misconception that a brown dwarf is like a pilot light that might catch given enough time, or that gravity will eventually compress it enough to start fusion if you wait long enough. But as we saw earlier, degeneracy breaks the cycle that would make that possible. There is no slow march toward ignition. There is only cooling. And cooling for a degenerate object leads nowhere. This is part of what makes brown dwarfs so quietly tragic as astronomical objects. They don't go out in a blaze. They don't collapse into something dramatic. They just fade away into the background radiation of the universe, carrying all the hydrogen they would ever need to shine, locked inside a core that will never reach the temperature to use it. The pilot light isn't waiting to catch. The pilot light went out billions of years ago, and the gas line is sealed shut by quantum mechanics. So the complete answer to our title question has multiple layers. Can a brown dwarf become a star? Possibly, if mass is added under the right conditions. Will every brown dwarf that gains enough mass automatically become a star? No. The internal degeneracy state can prevent ignition even when the mass exceeds the threshold. Can an isolated brown dwarf ever become a star on its own? Absolutely not. It can only cool and fade forever. Now let me take a step back and think about what this tells us about the universe and about the nature of the boundary between stars and brown dwarfs. We like to draw clean lines in nature. Star or not star. Planet or not planet. Living or non-living. These categories help us organize our understanding of the universe. They give us labels that we can attach to objects, and those labels carry meaning. When we say something is a star, we immediately know a set of facts about it. It fuses hydrogen. It has a stable luminosity. It will live for a certain amount of time depending on its mass, but nature doesn't always respect our categories. The boundary between stars and brown dwarfs is not a brick wall with one side labeled star and the other labeled not star. It's a gradient, a transition zone where objects can have properties that don't fit neatly into either category. An object with 74 Jupiter masses and solar metallicity is a brown dwarf. An object with 76 Jupiter masses and the same composition is a star. But the difference between them is tiny. They form the same way, from the same kind of material, through the same process. The one that became a star had just barely enough mass for fusion to sustain itself. The one that became a brown dwarf was just barely short. And when you add the complications of accretion, mass transfer, and mergers, the boundary gets even fuzzier. Objects can cross it in one direction, from brown dwarf to star, under certain conditions, and they might be able to sit above it without crossing it in practice, if their degeneracy history prevents fusion from taking hold. The boundary exists, and it's real, but it's not the clean, simple line that introductory astronomy courses often present. This fuzziness is not a failure of our understanding. It's a feature of nature. The universe is continuous, not categorical. Our labels are approximations, useful simplifications that help us talk about the natural world without drowning in complexity. But the natural world itself doesn't care about our labels. It just does physics. And sometimes the physics produces objects that don't fit comfortably into any box. Brown dwarfs themselves are a testament to this. They were predicted theoretically in the 1960s by the astrophysicist Shiv Kumar, who calculated that objects below a certain mass couldn't sustain hydrogen fusion. The name brown dwarf was suggested later by the astronomer Jill Tarter in 1975. But it wasn't until 1995 that the first unambiguous brown dwarf was confirmed observationally. An object called Gliese 229b, discovered orbiting a small red star about 19 light-years from Earth. For 30 years, brown dwarfs existed as a theoretical prediction, objects that should exist based on physics but hadn't been found. When they were finally confirmed, it validated decades of theoretical work and opened up an entirely new field of astrophysics. Today, thousands of brown dwarfs have been identified. They range from objects just below the hydrogen burning threshold, barely failing to become stars, to objects as small as a few Jupiter masses, barely distinguishable from giant planets. They orbit other stars, float freely through space, and occasionally form binary pairs with each other. They are among the most common objects in the galaxy, potentially outnumbering true stars, though their faintness makes them difficult to count accurately. Every one of these objects failed to become a star. Every one of them formed with almost enough mass, but not quite. And every one of them is now on the same irreversible journey, cooling, fading, becoming more degenerate with each passing year. Some of them might eventually gain mass through encounters with other objects. Most of them never will. They will drift through the galaxy for trillions of years, growing colder and dimmer, long outlasting the stars that currently blaze across the night sky. In the far future, when all the hydrogen in the galaxy has been consumed by stars or dispersed into intergalactic space, when the last red dwarfs have finally exhausted their fuel and gone dark, brown dwarfs will still be there. Cold, dark, degenerate, nearly undetectable. They will be among the last surviving objects in a dying universe, relics of a formation process that happened trillions of years earlier. They will carry within them the hydrogen that could have powered a star, but never did. Fuel that will sit unused forever, locked inside a degenerate core that no natural process will ever reignite. There's something poignant about that. An object that almost became a star, that had all the ingredients, that just needed a little more mass or a little more time in the right conditions, and then spent the rest of eternity slowly going dark, carrying unused fuel through a cold and empty universe. But there's also something remarkable about what brown dwarfs teach us. They teach us that the universe operates on thresholds, that there are tipping points where a small difference in initial conditions leads to a completely different outcome. A few extra Jupiter masses of gas in the original collapsing cloud, and the brown dwarf would have been a star, shining for trillions of years. A few less, and it never even burns deuterium. These thresholds are everywhere in nature. They govern which chemical reactions proceed and which don't, which planets develop atmospheres and which lose them, which collapsing clouds form stars and which form brown dwarfs. The universe is full of almost a star, almost a planet, almost alive, and the tiny differences between almost and achieved shape everything we see. So the next time you look up at the night sky on a clear, dark evening and see the stars scattered across the blackness, remember that for every star you can see, there might be several brown dwarfs you can't see, drifting through the same space, made of the same material, born from the same clouds. They are the ones that didn't quite make it. The ones that were a few percentage points short of the mass they needed. The ones that were almost suns. They're out there right now, invisible, silent, slowly cooling towards a temperature that will eventually match the cosmic background itself. They are the universe's great almost, a reminder that the difference between brilliance and darkness can be vanishingly small, and that sometimes, even when you're given a second chance, the physics of your own history can hold you back from crossing a line that was always only a few steps away. That is the story of the brown dwarf and its impossible dream of stardom. Not a simple yes or no, but a conditional answer shaped by timing, temperature, degeneracy, and the relentless forward march of cooling that turns an almost star into something that can never be undone. The universe doesn't always give clean answers, but the messy, complicated, conditional truth is always more fascinating than a simple one. And in the case of brown dwarfs, that truth reveals something deep about how nature draws its boundaries, not with sharp lines, but with gradients and histories and quantum mechanical rules that care nothing for our desire for simplicity. Thank you for joining me tonight on this journey into one of the most fascinating questions in astrophysics. If you found value in this exploration, a like or subscribe would mean the world to me. It helps this channel keep diving deep into the questions that make the universe so extraordinary. Sleep well tonight, knowing that somewhere out there in the darkness between the stars, a brown dwarf is slowly cooling, carrying within it the fuel for a fire that will never be lit. And that quiet, patient, endless fading is one of the most beautiful and melancholy truths the cosmos has to offer. Good night.